All right, good morning, everybody. I hope you're enjoying your first snow day, Group B. This video, it'll walk you through the notes that we would have done in class on the next section in your packet, so you should have this with you. If you don't, please let me know. I can get you copies, whatever you need. But today we're going to talk about some exponential growth and decay in terms of some real-world applications where you might see stuff like that. So if you remember, the base of a growth exponential has to be bigger than 1, right? We said it had to be bigger than 1. So what you're going to see in these problems is that they give you a rate in terms of a percent, like a percent increase. And so the growth is 1 plus that percent to keep that value bigger than 1. Essentially, the 1 is going to be like a placeholder and going to cause it to grow. The decay side of it has to be less than 1 but bigger than 0. So that base, what we'll do is we'll take the same rate, but we'll subtract it from 1 instead. And so you just have to make sure you know the difference between growth and decay. After that, it's just plugging everything in to the appropriate spots to figure out what's happening. So we're just going to work through these examples. So given the exponential model, y equals 200 times 0.8 to the x. Tell whether the model represents exponential growth or decay. Then tell what the growth/decay factor is and the growth/decay percent. So we're looking at the 0.80. That's where all of this information is coming from. Since 0.80 is less than 1 but bigger than 0, then this function is decaying. All right, there we go. It'll focus. The growth and decay factor, what would the percent be here? And so the factor is actually just 0.8. So it's decaying by a factor of 0.8. But what is that in terms of a percent? So the percent that decreased, remember it's 1 minus the rate that gives us the 0.8. So the rate that we took off was a 0.2 to get 0.8, which means that this was actually a 20% decrease. And so notice that an original question that would have had this equation has a 20%, and that's because it was 1 minus the 0.2, which gives the 0.8. So you just have to be careful in terms of what numbers you're plugging in specifically. All right, so next question. You deposit $1,500 into an account that pays 5% interest. Find the balance after 6 years. So you're looking for the balance, so you're looking for the amount in the account. The principal amount, the amount you start with, is $1,500. That's the number in the front, the starting amount. That's what the P is in both of these equations, is the principal or starting amount. It pays 5% interest, so this is going to grow. So because this is a growth function, it's going to be 1 plus, and 5% is 0.05. And you're probably okay, I'm assuming, turning those into percents. If you're not, just take 5 and divide it by 100 out of 100%. It'll tell you the decimal every time. And then it says find the balance after 6 years. So this is going to be raised to the power of 6. So what's going to happen is it's going to take this 1,500, multiply it by 1.05 6 times. And at the end of the 6th time, that would be our final balance. If you have a calculator at home, just a basic one, you don't need anything fancy, you can go ahead and do this calculation. If you don't, then you can always look on Google. Google has calculators that you can use. Desmos has a scientific calculator. I'll link it in the post so that you have access to some kind of calculator so that you can calculate this. So I just have my basic phone calculator here. So this would be 1,500 parenthesis 1.05. I did the addition in my head, and that's something I'm sure you could do. And then raise it to the power. So I want and the 6th power. So I'm going to hit this x to the y, and that makes it the 6th power. So this is 2010. And then because we're talking about money, you'll round it 2 decimal places. So 0.14. So $2,010.14. All right. So up next, the mice population is 25,000 and decreasing. So it's important to note that this is going to be a decay, decreasing by 20% each year. What will the mice population be after 3 years? So the amount or the population of mice, our starting amount is 25,000. It's decreasing, so it will be 1 minus for decrease. 20%, so 0.20, or you could just put 0.2, right? That's the same number. And we want to know after how long? After 3 years. So you can go ahead and calculate this using your handy data calculator, whether it's on your phone or computer. Should I clear that out? 25,000, 1 minus 0.2, which if you already know that that's 0.8, you just want to put in 0.8, that's fine as well, to the power of 3. 1,280. So after 3 years, it drops. I definitely messed this up because I forgot a 0. It's like, that doesn't make any sense. 12,800. There we go. I was like, how do we go from 25,000 to 1,280? So the number kind of helped me let me know I was a little off on my values here. All right. The number of mosquitoes at the beach has tripled. That is going to be important because that is a rate. And whenever you see the word triple, you should be thinking of the number 3, right? Tripled every year since 2019. In 2019, there were 2,500 mosquitoes. How many mosquitoes would you predict are at the beach in 2025? So the amount of mosquitoes, we start with 2,500. This question is a little bit different because they don't give us a percentage here. Instead of a percent, they just say that it triples. So the entire parentheses is not going to be 1 plus or 1 minus. It is literally just tripling, and tripling means it gets multiplied by 3. And so if it's not a percent and it's something like triples or doubles, you're going to want to just use that number straight up. You don't want to use 1 plus, 1 minus. 1 plus and 1 minus are going to be used when you have percentages that you're working with. All right, and then we need the power, so we have to figure out how many years is this. So we have 2019, that would be essentially year 0. So if you think about it, 2019 is year 0. So you have 20, 21, 22, 23, 24, and 25. Sorry, you can't see that. So if this is year 0, not year 1, because that's where our original amount comes from, and that's year 0, this would be 1, 2, 3, 4, 5, 6. And so what you could have done is just subtracted these two numbers. But if you're ever not sure, just write yourself out like a little timeline to get your accurate power. So that would be to the power of 6. So on your calculator, go ahead and calculate that. 3 to the power of 6. So I have 1,822,500. And it seems like a lot, but you're tripling. And so tripling is a pretty strong exponential growth happening there. So think about in the graphs that we made yesterday, if you're group B, or group A last week, right? If you made those graphs, that the triple is actually a pretty significant increase as you're going up. So that's not an unrealistic number. Mosquitoes. All right, I bought a car for $25,000, but its value is depreciating. Depreciating means that it is going down, it is decreasing. So this is a decay. So if you didn't know what depreciate meant, you kind of just need to know depreciating, decreasing, decaying. You could see that in future problems as well. So it's decaying at a rate of 10% per year. How much will my car be worth after 8 years? So the value of the car was originally $25,000. This is a percent problem, so we're back to the 1 plus or 1 minus. Since it's decay, it's going to be 1 minus. The rate, 10%, that's 0.10. to the power of 8. And so we can grab our calculator, calculate this. Make sure I include all the zeros this time. I'm going to go ahead and do that part in my head. I know 1 minus 0.1 is 0.9 to the power of 8. So 10,761. And then this is money, so that means I need to round to 2 decimal points for a dollar amount there. So it actually loses more than half of its value over those 8 years, even though it's only depreciating at 10% each year. But 8 years is quite a bit of time. So this happens 8 times. It goes down 10% 8 times. So that is definitely a realistic number here. All right. What you'll find is that many of these are going to be very similar kind of from here on out. I'll still do these last 5 with you. It would have had you try them in class and then we would have gone over them. So if you want to hit pause on the video, try them on your own, and then hit play again and kind of go over them, kind of simulate what we would have done in class. That's not necessarily a bad idea. If you're like, I'm still feeling a little iffy or whatever, and you want to just give them a shot with me, that's fine as well. So we'll just go ahead and keep working through some of these. All right, so find a bank account balance if the account starts with $100. So we're looking for the final amount, starts with $100, has an annual rate of 4%, and the money is left in the account for 12 years. So this account it's increasing is what's happening, is they're giving you interest. It doesn't really say that, but at no point does it say that they're charging you anything. So you have $100, your annual, this should probably say interest rate. I'll change that for next year. Annual interest rate of 4% left in the account for 12 years. So this is going to be a plus 0.04 because we're going to be adding money into this account, the interest, and that is for 12 years. So on our calculator, we can go ahead and calculate this. 100 parentheses, that's 1.04. Forgot my decimal. To the power of 12 years. $160. And then because we are talking about money, 2 decimal points. Anytime you're talking about money, round to 2 decimal points. All right. We're going to see, by the way, we're going to see some other account information, kind of some account balances and stuff, dealing with some, instead of annual interest rate, dealing with some other kind of interest rates. But if it's annual interest rate, it's just a basic exponential growth decay model. There's nothing fancy going on there. But we will see one that it might be like semi-annually or weekly or monthly, daily. So we're going to see some more of those in the future. All right, in 1995, there were 285 cell phone subscribers in the small town of Centerville. The number of subscribers increased by 75% per year after 1995. How many were there in 2010? So our original amount, 285. We're increasing, so that'll be 1 plus 0.75. How many in 2010? So how many years is it between? Well, that is 15 years. So I'm actually going to expect this number to be quite big because this is a pretty big percent increase, and that's quite a bit of time. So even though we start with 285, I would expect to see something pretty significant. So let's see what we get. To power 12, 235,126. Since we're talking about people here, you can go ahead and round it to the person. So that would be the whole number, right? Wouldn't make sense to have a 0.4 of a subscriber. But yeah, we went from 285 to 235,000 in 15 years, which is quite a bit of time, but we had a very strong growth percent there. So I would kind of expect that to happen. All right. An adult takes 400 milligrams of ibuprofen each hour. The amount of ibuprofen in the person's system decreases. That's important, decreases by about 29%. You're just going to roll 29% for this. How much is left after 6 hours? So you start with 400 milligrams. We're decreasing, so it'll be 1 minus 0.29 left after 6 hours. And then just calculate away. 400, 1 minus 0.29, and then power of 6. So 51. And then for decimals here, if you're not sure, you can always just take it to 2 to be safe. 2 or 3 is a pretty good estimate there. So 51.24. And that is milligrams left over. Which makes sense that this number is smaller than our original amount because this is a decreasing, it's going down. All right. Each year, the local country club sponsors a tennis tournament. The play starts with 128 participants. During each round, this is interesting, half of the players are eliminated. How many players remain after 5 rounds? So there's actually 2 ways to think about this. We have our starting amount. The first way you can think about it is half is that you're getting rid of 50%, right? So you can think of eliminating, so 1 minus 0.5 to the power of 5. Or another way to think about this is 128 starting, but your half the players are getting eliminated. So your growth rate is just 0.5 or 1/2 because it's being cut in half every time. So instead of like doubling or tripling, this is being cut in half, also to the power of 5. These are the same equation because 1 minus 0.5 is the same as a half. But either way you want to think about it, it will get you the right answer there. So when you're talking about half, you could think about it as 50%, or you could think about it as just a normal exponential without a percent going in here and just use 1/2. Either one, they're exactly the same though. So we have 128 times 0.5 to the power of 5. And that is 4. So there are 4 players remaining. Also, if you couldn't, like let's say you're taking the ACT or something and you couldn't remember, you could always just start with 128, cut it in half, so divide it in 2, you'd be at 64. That's 1 round. Cut it in half, you'd be at 32. That's 2 rounds. Cut that in half, you'd be at 16. And then in half there, that would be the end of the 1, 2, 3, 4th round. So the 5th round, you would have just 4 left. So this one you could also just go through each round and figure out how many people would be left. All right, and last but not least, you have inherited land that was purchased for $300,000 in 1960. The value of the land increased by approximately 5% per year. What's the approximate value of the land in the year 2011? So 30,000. We'll start. Increase, so 1.05, 1 plus 0.05. And we need to know how many years that is. Well, if you subtract them, that would be 51 years later. What is the value of the land? 30,000, 1.05 to the power of 51 years. So $361,223, and this is a value, a number, in terms of money. This is a money, sorry. And then so that would be 0.09. So 9 cents. All right, so hopefully those made a little bit of sense to you, not too crazy for your snow day, for your day off. So your homework assignment is the next page in your packet. There are 16 of them, and so you're just looking for the values at the end. So each one of these little boxes is its own little question. Typically, I do this as like an in-class activity, but obviously you're not in class today, and our activities can be limited anyways. So you're just going to go ahead and write the equation right here and then just put your answer. You don't have to show me really anything else, just the equation, answer, because I know you're going to just use your calculator to go ahead and calculate those. If you have any questions, please let me know. I am available to help. You can shoot me an email. Just if you email me at like 9 o'clock at night, just don't expect to get a response anytime soon, right? You'll probably have to wait till the next day. In terms of when is this due, it's due the next day I see you. So Group B, if I see you on Friday, if we're back in school on Friday, you'll turn in this right here, and you'll turn in the graphing problems. If you're Group A, if I see, I don't know Group A what the situation will be, but whenever I see you, if Group A is watching this, whenever I see you next, you're going to do the same thing, turn in this assignment and the graphing problems. But like I said, please let me know if you have any questions, and there will be a link to a graphing calculator, a scientific calculator for you in the post.